Hi, my name is Brianna Poon, and this is my lab report for Lab 3 circuits. So some fundamental principles I use in this lab are the node and loop rules, which say that the current flowing into a node must equal the current flowing out, and the round trip change in potential energy must equal 0 for any loop. And so I also use Ohm's law, which states that the delta V for resistors is equal to current times resistance, and in series, the resistance total is equal to the sum of each resistance. And in parallel, the reciprocal of that is equal to the sum of the reciprocal of each resistance. And for capacitors, delta V is equal to charge divided by capacitance, where capacitance is equal to epsilon naught times area divided by distance. So the purpose of this lab is to use fundamental principles of conversion of energy to predict the currents that flow through circuits containing resistors and capacitors, and use a computer model to observe the circuits and their actual behaviors. So the first part of the procedure involves observing the change in energy conservation in series circuits, and the second part involves the investigation of behavior of RC circuits. So the model here is my computer model, and the system is a circuit, surrounding is everything else. And I assume that the delta V of the wires is negligible because of the high electron mobility, and also that the delta V of the ammeters is negligible, and that the EMF of the battery is equal to delta V of resistors plus the delta V of the capacitors. So the initial conditions for part 1 are 2 batteries with an EMF of 3 volts, 1 resistor with 47 ohms, and a second resistor with 100 ohms. This should be 100. And so my current prediction work here is using the node rule, and that came out to be 0.02 amps, which matches the actual current reading. And if the ammeters were backwards, this would read negative 0.2 amps. And so here I replaced one of the ammeters with a voltmeter, and one of the remaining ammeter reads 0 amps, and then the voltmeter reads 3 volts. Oops. The ammeter reads 0 because the circuit is currently open, meaning there is no current flowing through, and the voltmeter reads 3 because the potential difference across the opening of the circuit is equal to the EMF of the batteries. And so here I measured the potential difference across different parts of the circuit, as shown by this diagram here, and then graphed what I observed in this model here. And then I summed all of those for the total potential difference, which came out to be 0, which supports the loop rule. And throughout this, the ammeter reading did not change because the voltmeter does not really conduct current, so there is no change to the circuit. And so lastly, I connected an ammeter in parallel with the 100 ohm resistor, and the current increased to 0.06 amps because of the node rule. Less current ends up flowing through the 100 ohm resistor, meaning that the resistance therefore decreases and current increases. And then I also recalculated the resistance of the following elements. Both of the resistors' resistances increased by small magnitude, and the wire and the ammeter were both 0. So for part 2, I used 2 bulbs, 10 and 20 ohms, and then a 9-volt battery and a capacitor of 0.02 farads. And so when I put the battery, bulb, and capacitor in series, the bulb will first light and then dim slowly. This is when the capacitor is charging and the current is decreasing from max to 0. And then when the battery was taken out, the bulb would do the same thing, but this is when the capacitor is discharging and the current decreases from max to 0. And so I also timed how long it took to charge and discharge for both bulbs, as shown here. And then finally, I measured the delta V for a 30 ohm light bulb using a charged capacitor, as shown by this graph here. And then use these following equations to calculate the RC of the circuit, which is the time constant. And I was able to calculate this using also my line of best fit. And my calculated RC came out to be 7.918 seconds as compared to the predicted RC, which was 6 seconds. So the calculated RC was higher than expected, meaning that there was some sources of error, likely none in the model since it was a computer model, but I probably had some error using the stopwatch or pausing the model inaccurately. So if I were doing this experiment in real life and use an actual ammeter instead of a simulated ammeter, a real ammeter has non-zero resistance, meaning that it likely would have decreased the current by a small magnitude. And if I were using a real battery to charge the capacitor with no resistor in the circuit, The ideal model predicts that the capacitor will fully charge almost instantaneously since there are no resistors and the whole circuit will increase in voltage until it matches the EMF of the battery. And this prediction would likely be similar in real life since copper wires have a very high conductivity, but in reality, their resistivity is not totally negligible, so there would still be some resistance. And that's the end of my presentation. Thanks for listening.